Okay, to carry on in this two-part video about empirical and molecular formulas, we want to turn our attention now to the molecular formula. This is the formula that we're most familiar with. So, as we saw in the previous video, in the previous section in this workbook, molecular formulas and empirical formulas are different concepts. A molecular formula and an empirical formula may end up being the same formula, as we saw with formaldehyde, but they can also be different formulas, as we saw with glucose. Molecular formulas represent the actual number of atoms, not just the lowest ratio of those elements in the compound. So let's take water as an example. Water is formed of a hydrogen bonded to an oxygen bonded to another hydrogen. So that's the structure. It has two hydrogens and an oxygen atom in it. So because the actual number of atoms in water has two hydrogens and one oxygen, the molecular formula of water is H2O. But this is also the smallest ratio of atoms, so the empirical formula of water is also H2O. Well, that's great if we actually have the structure of a compound, a structure of a molecule. We can easily determine its empirical and molecular formulas. But as we saw with the previous section, with the phosphorus and chlorine example, what happens if we don't know the structure of the molecule? Then we have to calculate the empirical formula. And similarly, we can also calculate its molecular formula. Now, in the previous video, I showed you how to calculate an empirical formula if you're just given the percent masses. In this video, we're going to get some practice doing that, but we're also then going to go on to the next step, which is then to calculate the molecular formula of a compound. Now, if we do not know the actual structure of the compound, we will not be able to just look at its structure and figure out its molecular formula. We can calculate the molecular formula if we have two pieces of information. If we are given the actual molar mass of the compound, and we have already determined the empirical formula, or we're given the empirical formula, either one. So you need these two pieces of information to be able to calculate a molecular formula. You need the actual molar mass of the compound, or an approximation at least, and you need the empirical formula, either because it was given to you or because you calculated it, according to the method that we discussed in the previous video. So we have a sample problem here now that we're going to work on. It says, in the previous section, in the previous video, you determined the empirical formula for a compound containing phosphorus and chlorine. Just as a reminder, here's that page where we did all that work, right? We did the percent to mass, mass to mole, divide by the smallest, and multiply to the whole number, and we got P2Cl3. So we have just done this work to calculate an empirical formula. So we have one of the two pieces of information that we need in order to now calculate a molecular formula. What's the other piece of information that we need? We need the approximate actual molar mass of the compound that we're dealing with. So let's go back to this. There we go. Now determine the molecular formula of the compound if its actual molar mass, and that's the other piece of information that we need, is approximately 337 grams per mole. So we now have the two pieces of information. We know that the empirical formula was P2Cl3. I'll put that there just so that we have it handy. And the actual molar mass is right there, right? Okay, so there are a few math steps in this, and here we go. Step 1, we're going to calculate the empirical formula mass. That is the formula mass of the empirical formula. So what would be the mass of this? And then basically we're going to compare it to the actual molar mass. Now, if those two values are the same, then we already know that that is the molecular formula as well. But if they're different, we need to know by what factor they're different. So for example, if we were to calculate this formula mass, and this actual mass were twice that formula mass, then we would know that we would have to multiply these subscripts by 2 each to get the actual molecular formula. But let's do that step by step so that we see how this works. Step 1, calculate the empirical formula mass by adding up all the masses in the empirical formula. So P2Cl3, let's do that down here. P2Cl3, that's the empirical formula. And I'm going to calculate its formula mass. 2 times phosphorus, 3 times chlorine, 2, 3, 35.453. I remember that one offhand. Phosphorus, 30.974. And this is either in AMUs for a single phosphorus or it's grams for a mole of phosphorus. We're dealing with molar masses, so these will be in grams now. So let me do this math. And 61.948 grams per mole. Or that should just be grams, sorry, grams. That is being contributed to that molar mass for that. And the 3 chlorines, 106.359 grams. And you may recall that this is an example that I told you about earlier where the multiplication rule of sig figs says that I would take the smallest number of sig figs. That's an exact number, 5 here. So typically the rule would say to only have 5 sig figs in my answer. And here I've got 6. So what happened? Well, I can also conceive of this multiplication problem as just an addition problem where I'm adding this number to itself 3 times. And if I think of it as an addition problem, you can see I should be able to keep my precision out to that 3rd place past the decimal, that thousandths place. So that's why I kept it there, okay? Something to consider when you're doing these molar masses so that you don't throw away precision that you should have. Then I'm going to add that up. So 168.307 grams, and that is per mole of that empirical formula. So we have determined the formula mass, the molar mass of the compound if that were its formula. But let's compare it to the formula they gave, the actual molar mass, which is 337. And you can see that the actual molar mass is about double that empirical formula mass, which tells me right away that this is not the actual molecular formula, that they're different and approximately by a factor of 2. So right away, I can tell that my actual molecular formula is going to be probably P4Cl6. It's going to be double that. But let's go through the steps and see. I'm just going to draw some lines here to separate my math. So we've done step 1. We've calculated the formula mass for the empirical formula. Step 2, we're going to divide the actual molar mass by the empirical formula mass. And this is going to give us a new scaling factor that relates those two formulas together. And we go ahead and round the scaling factor to the nearest whole number. Okay, so this is step 1 over here. Now I'm at step 2. And I'm going to divide the actual molar mass, which they say is approximately 37 grams per mole, by my empirical formula mass, by 168.307 grams per mole. And that's going to tell me by what factor the two formulas are different. And you can see that it's about a 2. And my calculator says that it's 2.0022. It doesn't really matter what those other digits are because I am going to round the scaling factor to the nearest whole number anyway. So this is going to equal a 2. That's my scaling factor, right? That is the factor that relates the two formulas. So it basically says that the molecular formula is 2 times whatever the empirical formula is. Step 3, multiply the subscripts on each atom in the empirical formula by the scaling factor. These new values are the subscripts in the molecular formula. So if 2 is my scaling factor, times 2 is I'm going to get P4. 3 times 2 is 6, Cl6. And now I have my molecular formula. The empirical formula, the lowest ratio of atoms. The molecular formula, the actual number of atoms in that compound. Okay, so in the previous video, you calculated an empirical formula, and in this video, you use that information and the actual molar mass of the compound to then calculate its molecular formula. So we've gone through both of those, and now, ta-da, it's your turn. So here's a sample problem, and it's got 2 parts, A and B. Part A says, determine the empirical formula of an unknown compound, given the compound was found empirically, that means by doing an experiment, to be 89.9% carbon by mass, the mass percent of carbon, 89.9%. And the remainder of the percentage, which we'll have to figure out, is hydrogen. So you're going to have an empirical formula that has carbons and hydrogens in it, and you're going to have to calculate that empirical formula using the method that we learned in the previous video. That's part A. So the goal of part A is to determine the empirical formula. Part B, then, once we have that empirical formula, we determine the molecular formula of this compound if its actual molar mass is approximately 80 grams per mole. And you're going to use this method that we just learned in this video to go from the empirical formula and its approximate molar mass to get to the molecular formula. So here on the page, I haven't given you a whole lot of space, so be kind of parsimonious, careful with your space usage. If you need to use a scrap piece of paper to do that, that's fine. But I want you to do this sample problem, see how you do. So remember, it's a 2-part problem. Part A, determine the empirical formula. Part B, use that information and the approximate molar mass to determine the molecular formula. Okay, so go ahead and pause the video and do that work. And when you're done with this, resume the video and I'll show you working through it. All right, go for it. All right, so coming back from pausing the video, I'm just going to separate my workspace here so that I know that I've got part A and part B that I'm going to have to work on. Here we go. Okay, so part A, determine the empirical formula of an unknown compound, given the compound was found empirically to be 89.9% carbon. And the remainder is hydrogen. Well, if the remainder is hydrogen, then it must be 100 minus the carbon percentage gives me hydrogen. So I can do that in my head, or I could do it on a calculator, but it's essentially going to be 10.1. So 89, 99, and there we go, we got our 100%. So there's my percentage of the hydrogen. Now, remember the 4 steps. Percent to mass, mass to mole, divide by smallest, multiply to whole. The last step may not be necessary. So here we go. Percent to mass. Just no math here. That's why I'm doing the swoopy arrow, just to say, and then magic happens. And I suddenly have 89.9 grams of carbon. And then 10.1 grams of hydrogen. Now I'm being a little bit facetious here. I'm not doing any magic, nothing tricky. I'm just saying, assume we have 100 grams of this compound, then whatever the percentage is also equal to the number of grams because I've made that assumption. And it works, okay? There's my first step, percent to mass. My next step, mass to mole. Oops. So we're going to do that times grams of carbon to moles of carbon. We know molar masses are always per 1 mole. Grams of hydrogen to moles of hydrogen. And that's per 1 mole. Carbon's molar mass is 12.011. Hydrogen is 1.0079. And so I convert these gram values to molar values. Let me do this math. My answer for the carbon is 3 sig figs, 7.48 moles of carbon. Number of moles of hydrogen is 10 point, and it's 3 sig figs, 10.0 moles of carbon. Okay? Percent to mass, mass to moles. What's the next step? I divide by the smallest number. Okay, and it's going to turn one of these numbers into 1, right? And the other number, it will be some ratio in relationship to that 1. 10.0 divided by 7.48 equals 1.34. And that's moles of carbon to moles of hydrogen. So you can see I'm starting to get the ratio here in simpler numbers. Now, step 4, do I need to do step 4? I only need to do step 4 if any of these numbers is further away from a whole number by 0.1 or more. That one is that one is a whole number, so I'm good there. But this one is not. It's not within that margin that I've allowed myself of 0.1. It's 0.34 away from being a whole number. So do I need to do step 4? Yes. And what is step 4? I multiply both numbers by some scaling factor until I get them close to a whole number. Whatever I multiply one by, I absolutely have to multiply the other by. And this is a common error that students make on this problem. They'll multiply this one by a scaling factor to get it to a whole number, but they won't multiply this number as well. But you have to do it to both of them. Well, I think you can see that if I multiply both of these by a scaling factor of 2, it's not going to get this one close to a whole number. But if I multiply them both by a scaling factor of 3, it will get this one close to a whole number. So I'm going to use 3. And if you have to plug it into a calculator to see how this works, you can use some trial and error, but eventually, after you do this a couple times, you'll start to pick up on those cues, and you'll develop that intuition to see what your scaling factor should be. If I do it to one, I have to do it to the other. Okay, this one becomes 3.00, and this one becomes 4.02. Notice that both of these numbers are now within 0.1 of being a whole number, either higher or lower. So those whole numbers are now going to be my subscripts. So carbon has a 3, hydrogen has a 4. And that is my empirical formula. So I've solved the first part. I've gotten the empirical formula of this compound. Percent to mass, mass to moles, divide by the smallest, and then multiply until they're all whole numbers. All right, so now I have to do part B of this problem, which is determine the molecular formula of the compound if the actual molar mass is approximately 80 grams per mole. So I know that C3H4 is the empirical formula. That's the lowest ratio of atoms. Now I'm going to figure out the molecular formula, the actual number of atoms. So I go through my 3 steps. I calculate what that empirical formula mass would be. So C3H4, so I got carbon times 3 times carbon equals, and 4 times hydrogen equals. But in the addition now, when I add these, I cannot go out to the fourth place past the decimal. So there is my empirical formula's mass, the formula mass for the empirical formula, 40.065. And right away you can see that it's about half of what I was told that the approximate molar mass is. So hopefully you're starting to develop the intuition now that you might start to recognize that this formula should be doubled to get my molecular formula. But let's go through the math. Let's do the diligent steps here. Step 2, I'm going to take the actual molar mass of the compound, which is 80 grams per mole, and I'm going to divide it by the empirical formula mass that's been calculated. And my answer is 1.996755. I'll go ahead and write all that out, 1.996755, fourth, and so on. But the rule here is that once I get this number, I just go ahead and round it to a whole number, whatever it is. This number doesn't have to be within 0.1 of a whole number. It's already going to be pretty close, so I just go ahead and assume that it's the closest whole number. And that's my scaling factor that I then multiply my empirical formula by. So C3 becomes C6, right? And H4 multiplied by 2 becomes H8. And now I have my molecular formula. So I calculated my empirical formula up here. That's the lowest ratio of atoms. And my molecular formula down here. So let me just label this work so that it's obvious what I was doing. So empirical formula. And this is my molecular formula. All right, and there we go.